This is Algebra 2, Unit 4, Lesson 6 on exponential modeling with percent growth and decay. Now, exponential functions are very important in modeling a variety of real-world phenomena because certain things either increase or decrease by fixed percentages over given units of time. We saw this in Algebra 1, so let's see if we can review how we do this. Alright, so suppose that you deposit money to a savings account that receives 5% interest per year on the amount of money that is in the account for that year. Assume that if you deposit $400 into your account initially. Okay, so basically what you're going to do is you're going to put money in the account, and then every year you're going to get 5% interest. Okay, now how much will the savings account increase by over the course of the year? Alright, so you're starting with $400, and then you're going to receive 5% interest. So we're going to multiply by 0.05. Remember, 5%, you move the decimal point 2 places, is 0.05. So if I multiply 400 times 0.05 is $20. So that's going to be $20. Now, how much money is in the account at the end of the year? So you started out at $400. After 1 year, you've earned another $20 in interest. So now you have $420 in your account. Okay, now having to do this every single time can be monotonous, and can be really confusing. So let's think about this for a second. By what single number could you have multiplied 400 by in order to calculate your answer in Part B? It has to do with what percent you're getting when you're done. All right, let's think about this for a second. You started with $400, and then you added in 400 times 0.05 as your interest to get your total amount. All right, if we look at this as a GCF, what's our GCF between these two terms? Would be 400. 400 times 1 plus 0.05. What's 1.05? That is the number that we would end up with. So 400 times 1.05 is equal to 20. Or is equal to 420, I'm sorry. Okay, now that makes sense when you think about it. If you are taking the whole amount, that's 400, isn't that 100%? And then you're adding in the 5% interest. When you're done, you have 105%, which is 1.05 as a decimal. That's 5. It's 1.05 as a decimal. So instead of having to start with your value, multiply by 0.05, add it back in, take that answer, multiply by 0.05, and add it back in, go on from there. If we just did in our calculator 400 times 1.05, there's our total amount without having to figure out the interest separately. So you have to think of it as 105% is an increase. So the overall increase is 105%. All right, so using your answer from Part C, determine the amount of money in the account after 2 and 10 years. Okay, so we have 400 times 1.05 would be 105% after 1 year. What would we multiply by for 2 years? Well, we multiply that answer by 1.05 again. So couldn't we say that's 400 times 1.05 squared? Yeah, so let's see what that is. 400 times 1.05 squared. And I end up with $441. So after 2 years, I would have $441. So what do you think after 10 years? It would be 400 times 1.05 multiplied how many times? It would be 10 times. So 400 times 1.05 raised to the 10th power. So rounded to the nearest cent, it would be $651.56. So it would be $651.56. Okay, so notice the pattern here. Give an equation for the amount in the savings account S of t as a function of the number of years since $400 was invested. All right, now remember this is an exponential function. So S of t, we need our starting value, which is 400. What is our multiplier? What are we multiplying by every time? We're multiplying by 1.05, and t would be the number of times that we multiplied it. So 400 times 1.05 to the t. So now that we have that function, using a table on your calculator, determine to the nearest year how long it will take for the initial investment of $400 to double. Provide evidence to support your answer. Okay, so I'm going to use my table on my calculator. All right, so I'm going to my calculator. I'm going to go to y equals. I'm going to put in 400 times 1.05 raised to the, we're going to use x instead of t, but that's okay. All right, then I want to go to my table. All right, I want to see how long it's going to take for the investment to double. Okay, so what number am I looking for in the y column? I'm looking for $800. All right, so if I look here for my values, where does it hit $800? Well, it's somewhere in this section right here. 14 years would be this much money. 15 years would be $831.57. So that means our initial investment here will double if you have, after 14 years, we have $791.97 in your account. After 15 years, you would have $831.57. Okay, so how long will it take for the initial investment to double? Well, it will take, to the nearest year, it's got to be over 14 years but less than 15 years. So it would have to take 14 years, approximately. It would take up to 15 years to double, but at 14 years, it would not quite be that, so it's a little more than 14 years. Okay, so there we have it. So the table, we can see that's going to be 800 after about maybe 14.2 or 14.3 approximately would have us the amount. So it's going to take at least 14 years to double, but 15 would be definitely doubled. So it's be 14 to 15 years. Okay, so that is exponential growth. So if we look down here, if quantity Q is known to increase by a fixed percentage P in decimal form, then Q can be modeled by this. Q of T is equal to Q of 0. Remember, Q of 0 is the amount of Q at T equals 0, and T is the time. Notice this is 1 plus P because that's the percent. So P is the percent, and it's 1 plus P because it's increasing. So it's 100 and whatever percent that you happen to have. All right, so which of the following gives a savings S in an account if $250 is invested at an interest rate of 3% per year? Okay, so if it's 3% per year, by how much does it increase after 1 year? It would be 103%. So we would multiply by 1.03. So it would be S is equal to, what's our starting value? It's $250 times 1.03 raised to the T over time. So that would be number 2. Be very careful. Remember, it's 2 decimal points for 1.03. All right. Decreasing exponentials are developed the same way but have the percent subtracted rather than added to the base of 100%. So just remember, you are ultimately multiplying by the percent of the original that you have after the time period elapses. So if something is decreasing, you're going to have less than 100% when you're starting that. So if you have your multiplier here, if you're going to decrease the quantity by the percent listed, what would you multiply by? Well, if you're decreasing by 10%, you would take 100% minus 10% would be 90%. You'd have 90% left. 90% would be 0.90. All right? If you are decreasing by 2%, what percent would you have left? You would have 98%, so it would be 0.98. All right, 25% would be 1 minus 25% would be 75%. You'd have 75% left. And 0.5%, be very careful on this one. This is 1 minus 0.005. Remember, because there's 2 decimal places, 1, 2. 1 minus 0.005 would be, you'd multiply by 0.995. All right, because what you start with and what you end with, because you're decreasing, would be less than 100%. So if quantity Q is known to decrease by a fixed percentage P in decimal form, then Q can be modeled by Q of T equals Q of 0, where Q of 0 is the amount of Q present at 2 equals 0, and it would be 1 minus P raised to the T. So let's try out an example of this. if the population of a town is decreasing by 4% per year and started with 12,500 residents, which of the following is its projected population in 10 years? Show the exponential model used to solve this problem. All right, so our exponential model that we have, what is our starting number of residents? Well, it would be 12,500. All right, now it is decreasing by 4% each year. So do we add or do we subtract? We would subtract. All right, so what percent are you going to have left if you take away 4% every year? Well, it would be 1 minus 0.04, which would be 0.96, so it would be 96%. You'd have 96% left every year. So whatever x would have, I'll do a y equals. All right, so which of the following is its predicted population in 10 years? Well, x would be 10. So it would be 12,500 times 0.96 multiplied 10 times. And if you multiply that out, 12,500 times 0.96 raised to the 10th power. And you'd have approximately 8,310 people in the town, approximately 8,310 people. So that would be number 4. Okay. All right, let's save number 5 for class, and we'll take a look at this one and the functions. So increasing and decreasing exponential models, it's the base, and it's either 1 plus or 1 minus if you're increasing or decreasing for your multiplier. Okay, let's save number 5 for the next class.